Nice.
since Will isn't here. All right, so here,
this
let's
for
talk
Will.
about kind of how this deal is gonna play out. So, this is what I'll sometimes do, I'll kind of give you like an ish answer. So like, for example, your number 5, that answer to number 5 should be around 30-ish meters, okay? Which, if you think about it, is, I mean, you're driving along and you look down and that's like 1.75 seconds, 1,001, 1,002, that's how long it would be. And you're basically gonna travel a third the length of a football field during this time. So that's why I was like, oh, hey, don't text and drive. Like, literally, if you have any kind of speed at all in that car and your eyes are distracted, it isn't, if you do the math, you are gonna travel quite a ways in that little bit of time it takes you to look at that screen, and a lot can happen during that time. All right, so let's talk about the rocket, okay? So here's,
Nice rocket.
thanks, years of being bored in physics lectures and getting good at doodling. So there's the rocket, here's your velocity time graph, okay? So there's a couple of different ways you can represent what's going to happen with this rocket. So start with this idea. What's the initial velocity of the rocket?
0.
0. It's sitting here on the launch pad, okay? So you know your velocity time graph is going to start at 0, okay? That's where it's at. We're not orbiting in space already. We're on Earth, sitting on a launch pad. So what's the whole point of the engines on the rocket?
Accelerate.
To make it accelerate, okay? And again, here's the story. And you remember this. Week from today, you're going to have your first big test. What are the only 2 options you can have when something accelerates?
Speed up.
Speeds
up
up
or slows down.
or slows down. That's it. That's it. Either on a velocity time graph, that line is going away from 0 or it's going towards 0. That's it. Okay? That's it. Unless you're specifically, and I mean specifically told that you're at a constant velocity, you're either speeding up or slowing down. That's it. So, you're going to fire the rocket engines. Now, you're told that the acceleration is a positive 5 meters per second squared. Oh, okay. So, some people like to think of acceleration as meters per second per second. So, this is how much money.
It's Will.
I left my name tag in my car.
Okay. Let's just keep recording it in case somebody in the 4th block is gone. So, some people like to make this analogy like money. Like you're earning you have a job, which would be a sweet job. You're making $5 per second, okay? And you started off with no money. At the end of 1 second, how much money have you made?
$5.
$5,
Nice.
okay? So, what we're saying here, and again, acceleration, and listen to me, acceleration is not how fast you go. Acceleration is the rate at which your velocity changes. So at the end of 1 second, how fast are you going to be going? 5 meters per second. At the end of 2 seconds, you're going to be going 10. So the slope of this line is going to be 5 meters per second squared. Okay, so that's one way to represent the motion. Okay, the slope of the line of your velocity time graph. That's one way. A lot of time, and this is going to play out in the lab that you're going to do today. You can also look at it in terms of what we call a motion diagram. So you fired the engines, and it's going to start off with some small velocity. Okay, I don't know what it is. I don't care what it is. It's some velocity. And again, here's your choices. One of 2 things is going to happen when you draw the next rocket. When you draw the next vector diagram. It's either going to get bigger or it's going to get smaller. That's your only options. Okay? It's either going to get bigger or it's going to get smaller. So what's it going to do?
Get bigger.
It's going to get bigger. So just come in here and go, oh, okay, cool. There's V2. V3 would be even bigger. Okay? So while that rocket engine is being fired, you're going to have some positive acceleration, which is going to make it gain a positive velocity. Okay? Now, we'll talk more about this later when we get into forces. There's a concept that I talk about called Jedi Stofawah. And Stofawah means stop the force and watch what happens. Okay? That's what the Stofawah part is. Stop the force, watch what happens. So, if I take this golf ball and I stop applying the force from my hands and I watch what happens. So, if I do that, what does the ball begin to do? As soon as it leaves my hand, what does it begin to do?
Slow down.
Slow down. Okay? It begins to slow down. Now, we'll eventually talk about all of Newton's laws. First law says objects actually don't want to slow down. Objects want to keep moving at a constant velocity until an outside force acts on them. So, if I stop the force from my hands and I watch what happens, and I see that ball begin to slow down, I know there has to be a force acting on it. Because if there wasn't a force acting on it, that ball would continue to go up at a straight line at a constant speed. Okay? And it would not slow down. So as soon as I see that ball start to slow down, it's like, ooh, there has to be a force acting on it. And that force is going to be what?
Gravity.
Gravity. So, here's the story. So at this point, I shut off the engines, right? I shut off the engines. So what's that velocity vector then going to begin to do? Again, you shut off the engines. It's a two-trick pony. Either that vector is going to continue to get bigger, or that vector is going to get smaller. What's it going to do?
Get smaller.
It's going to get smaller. Oh, it's going to go, oh. Then I'm going to start drawing vectors that are still pointing up, but are smaller. That's all you have to do on the motion diagrams. Okay? That's it. Now, let's talk about the acceleration vectors. Your acceleration vectors, relative to your velocity vectors, there's only two choices. Either your acceleration vectors point in the same direction as your velocity vectors and you speed up, or your acceleration vectors point in the opposite direction and you slow down. That's it. There is no, they're going to point in the same direction, but it's going to slow down. No. So here's the story. So when that rocket engine is being fired, and that's like me holding this thing in my hand and throwing it up when it's in contact with my hand, what's the direction of your acceleration? Upward or downward?
Up.
Up. Oh. So I'm going to have some positive acceleration. Okay? That's it. Now, when you shut off the engines, now what's the direction of your acceleration vector?
Down.
Down, because now it's in the opposite direction because it's slowing down. That's it. So when y'all do the lab today, you remember this. You're going to push a cart up an inclined plane, and you're going to watch what happens. And again, either the cart's going to be speeding up or the cart's going to be slowing down. If the cart's speeding up, the acceleration vector points in the same direction. If it's slowing down, the acceleration vector points in the opposite direction. That's it. That's literally, everybody goes, physics is tough. No, you either speed up or slow down. It's a binary function. Now, on your velocity time graph, because you're told that you're going to do this for 8 seconds, right? So if you like the monetary analogy, no one has a job that pays them $5 per second.
Yes.
Okay? At the end of 8 seconds, how much money have you earned?
$40.
A 40 spot, right? So he's got a 40 spot at this point. So at this point, he's traveling 40 meters per second, or he has $40, however you want to think about it. Now, at that point, Cohen says, I got money, and being the good American citizen that he is, I got to spend it. Okay? Now, he earned at $5 per second. But he's going to spend it, and again, being the good American that he is, he's going to spend it at $10 per second.
Yeah.
Welcome to America.
One McDonald's order.
So, yeah, not only do we have houses, we have an entire industry where you store stuff in storage units because you have so much stuff it won't fit in your house. So, now, you have $40, Cohen.
Nice.
You're going to spend $10 per second. How long is it going to take you to run out of money?
4 seconds.
4 seconds. So here's the story. Now, this line is gonna start to approach zero, okay? Because, again, what's the rocket gonna do? It's gonna, when you shut off the rocket engines, it's gonna do the Danny 3. As soon as you shut off the rocket engine, what's it gonna start to do?
Slow down, stop,
And then it's going to stop, and then it's going to start to fall and
accelerate.
speed back, re-accelerate. Actually, the acceleration is just going to be the same the entire time
Yeah.
once you shut off the engine. So this line is going to do something like this. Okay? Now, here's the other thing. We talked about this yesterday. F equals ma. Mass of the rocket, for now, we're going to assume is constant. In reality, it's not because it's going through fuel, but we'll talk more about that later. So here's the story. That means acceleration and force have to have the same sign. So the only way, and this is the bigger picture, the only way you can change the slope of a velocity time graph is to change the acceleration. The only way you can change the acceleration is to change the force. So initially, you had a positive force acting on the rocket, creating a positive acceleration. You shut off the rocket engines, the only force left acting on it is gravity. Now, that gravity is now going to be a negative force because it's acting downward. And it's going to create a negative acceleration, which is going to make that rocket slow down. So there you go. Anyway, so there's that. Any other questions on that whole thing on number 6? I promise you, you're going to have a question similar to number 6 on the test a week from today. I promise you, okay? I promise you. Make sure you understand the problem.
How similar?
It's going to be a little bit more complicated because you're actually going to have to calculate accelerations and stuff like that, but it's going to be the same concept. Okay. Your answer to number 7, it should be a really, really, really big number because this is how far a beam of light travels in a year. That answer to number 7 should be something times 10 to the 15th.
Oh, thank God.
Like that number?
Yeah.
Oh, on number 8 with the trip to the moon, and we'll talk more about what I'm going to kind of work this in, but there's this concept of significant digits. So your answer to
Ooh, yeah, actually.
both of your answers to number 8 should be something times 10 to the 3rd. Okay? So on number 8, you kind of have sketchy data. How far is it to the moon? Oh, 3.8 times 10 to the 5th. It took you 3.00 days. So all of those measured values have 3 digits in them. So that means your answer should only have like 3 digits. But the problem is, you view your calculator as an oracle, and like the oracle has spoken, and it's going to give you this whole display of numbers, and you feel a moral obligation to write them all down, because otherwise you think the calculator gods are going to get upset with you and won't give you the correct answer the next time. Your calculator does not care how many digits you write down. So, for example, that first answer in number 8 should be about 5,280. So you could write it as 5,280, you could write it as 5.28 times 10 to the 3rd. You could do 5.28 e to the 3rd. I don't care, okay? Something like that. Now, let's talk about number 9. It says, in what circumstances would it be necessary to use a tangent line on a position time graph? What could you determine? So here's the story. If you have a position time graph,
Or acceleration at that point.
and you have a straight sloping line, harken back to your geometry days. You think you could draw a tangent line to a straight sloping line? No. You can't draw a tangent line to a straight line. You can only draw a tangent line relative to a
Curved line.
curve. Oh, okay. So first off, you can only draw tangent lines if you have a curved line on a position time graph. Now, if you have a curved line on a position time graph, you're either at constant velocity or you have accelerated motion. Which one is it?
Accelerated motion.
Why?
Because your rate of change is changing.
Well, yeah, your velocity is changing. Don't make it complicated, right? Because if the slope represents velocity, and, which it does, and if the slope is changing, therefore the velocity is changing, therefore you are accelerating. So the only time you draw tangent lines is when you have a curved line, okay? So you might say like, hey, what's the velocity at 1 second? So you come up here, you draw a tangent line, and what that allows you to find is the velocity at that instant in time. Sometimes it's called the instantaneous velocity. So on that answer, you only draw it when you're accelerating, or you can say when the velocity is changing, and that allows you to determine the velocity at that instant in time. Okay, now, let's talk about 10 and 11. So, on number 10, here's the story. Like this morning, there was a nice thunderstorm, so there was a flash of lightning. So you see the flash of lightning, and it's 1 mile away, and the speed of sound is 3.3145 times 10 to the second meters per second. And later on, you see that the speed of sound actually changes depending on temperature and humidity. So here's the story. And you are 1 mile away, which is 1.609 kilometers. And you want to know time. So let's just start with this idea. You have meters per second and you have kilometers. What are you going to have to do?
Get your kilometers into
Yeah, change the
meters.
kilometers to the meters, or change the speed into kilometers per second. Okay? Let's just go with the idea that you're going to change that into meters, multiply by 1,000, you get 1,609. Now, meters. So let's just start with this idea. It's going to travel 1,609 meters. The speed of sound is about 331 meters per second. So does your answer to number 10 have to be bigger or smaller than 1 second?
bigger.
Bigger. Why?
Because 1609 is bigger than 331.
What'd you say? A little bit louder, Anna.
Because 1609 is bigger than 331.
Exactly. Okay? You have to travel a distance bigger than 330 meters. So you know your answer to number 10 has to be bigger than 1 second. So I'll show you 3 ways you can do this problem. One is you can do distance equals velocity times time. You know the distance, you know the velocity, solve for time. That's option A. Option B is, oh, Mr. Burkamp, I like ratios. Okay, you got 3.3145 times 10 to the second meters per 1 second is going to equal 1,609 meters over X number of seconds. Okay, set it up as a ratio. Oh, cross multiply and divide. You can do it that way. If you like ratios, cool. Set it up as a ratio. You go, Mr. Burkamp, I like geometry. Fine. Think of it as a velocity time graph. You have a horizontal line on your velocity time graph of 3.145 times 10 to the second meters per second. Now, how does that 1609 fit onto that velocity time graph? Yeah, that's an area. Oh, that's 1609 meters. So you know the area of a rectangle is length times width. Oh, there's your area, 1609. That's your width or your length, whatever you want to think about it. You're trying to find the time. So you can use a formula, you can use a ratio, you can do geometry. So your answer to number 10, and this is an ish, should be around 5 seconds. It's an ish, something around there. Your answer to number 11 would make a horrible GPA. Okay. Make sure on 13E, when I tell you to use arrows to indicate that something's speeding up or slowing down. So like here's this graph, boom, da-da-da, okay? Here's 0 meters per second. So there's a couple of ways you can think about this. You can think about it as terms of sign of velocity and acceleration. You can just look at it relative to the 0 meters per second line. Well, if you're starting at 0, what's the only thing you can do?
Speed up.
Yeah, so you know in this first region, you're going to speed up. Now, in the second region, you have a horizontal line on a velocity time graph. Does that mean that you're at rest, or are you moving with a constant velocity?
Constant velocity.
Constant velocity. Now, this line begins to approach 0. What are you going to be doing?
Slowing down.
Slowing down. So you just keep going with that pattern, okay? Any other questions on that assignment? Going once? Twice? Oh, Dan, yes, you're on.
Sorry. Can you like re-explain F or 6F again?
Which one?
6F.
6F?
Yeah.
Okay. So, draw the line showing the motion from the point at 8 seconds where the engine shut off to the point where the rocket is at its maximum height. So this is what you got going. So this was the initial 8 seconds, okay? And that was the slope of that line. So for every 1 second that goes by, your velocity changes 5 meters per second.
Okay.
So 5, 10, 15, all the way up to 40. Now, at this point, I shut off the rocket engines. One of 3 things is going to happen to that rocket. Either it's going to continue to speed up, it's going to reach a constant velocity and just go across like this, or it's going to begin to slow down. What's it going to do?
Slow down.
Slow down. And it's going to slow down at the rate of 10 meters per second. So if you start at 40 to get to 0, because that's when it's at its maximum height, that's when the velocity is 0. If you were to do that, it's just like Cohen. Cohen has $40. He's going to spend $10 per second. How long is it going to take him to run out of money?
4 seconds.
4 seconds. So you're here at 8, so you're going to end up at 12. So this line's going to end up at 12 seconds because you have to keep a running clock. You have to keep a total amount of time. Does that answer the question, Danny?
Yes.
Okay. Anything else? Go once, go twice, sold. Okay. Staple your graph to the back, get those handed in.
I slept funny and now all of me hurts.
Okay, so let's talk about the lab that you're going to do today. So, as we get into the heart and soul of acceleration, there's a couple of misconceptions that I have to get you to do an exercise on. And that's the whole purpose of this lab today, is that you all want to associate negative acceleration with slowing down and positive acceleration with speeding up. And that can happen, okay? But that isn't the main part of the story. So here's what you're going to do. You're going to, 8 of you, 2 groups of 4. One of you May South people is going to have to cross over to the Eagle side, okay? I'm just saying, it's okay. It's not that
You're
big.
ruining our bloodline.
Huh?
You're ruining the bloodline.
It's okay. Now, in terms of the lab itself, here's going to be your technique. You're going to set it up where you're going to put a block underneath one side, and then what that's going to do is create an inclined plane. So Galileo was the first one to use inclined planes because it allows you to make observations on the influence of gravity, but it's like watching it in slow motion. So if I throw this up in the air, oh, that happens pretty quickly. It's tough to make good observations. But if I can take this on an inclined plane and give it a push, it's like you're watching it, but you're watching it in slow motion. So here's the story. On these ramps, they already have like a meter stick glued on the side. So you're gonna have 0 here, you're gonna have 122 up there. We're gonna use these a lot. We'll use them in optics, we're gonna use them on motion, a whole bunch of different things. So set it up where the bottom side 0 is what you're gonna be going away from. So you don't have to, you could make this in the reference point, you can make this in the reference point. Pick one, okay? So if you make this in the reference point, you're gonna say, oh, it goes towards the reference point and then it comes back. If this is the reference point, it goes away, I don't care, pick one, okay? So once you get that established and you get this set up, I've got an app on my phone, or if you guys can use your phones, because we're gonna need stopwatches and timers and things like that. So you need this angle, okay? So once you get it set up, either call me over, or if you have the app on your phone that has a level, but it needs to go to like the nearest 10th, okay? So if you're gonna use your level, make sure it goes to the nearest 10th. So here's the story. So you're gonna be like this, and you're gonna give it a push until it goes, well, that was a good one, up and back. So what you wanna do is have 2 people timing this thing. And you want to time it from the second that it leaves your hand until it gets back to that point. Okay, don't just time it on the way up, or just don't time it on the way down. Time it from start back to that point. So you also need to observe the initial position of the cart when you let go of it, and then where it ends up. So you need to have somebody watching that. Now, here's the decision that you need to make. Either decide to go off the front of the cart, like where the front of the cart is when you let go of it, and then watch where the front of the cart is up here, or go off the back of the cart and then watch where the back of the cart is. You can't switch it, or otherwise you're going to be off by the length of the cart. So either say we're going off the back, and I'm going to watch where the back is going to go, or you're going to go off the front. Doesn't make any difference. Just make sure everybody in your group is going off the same page. Okay. Now, let's chit chat. So, what we're not going to do is include the push. Okay? So, we're going to start this analysis from the second that it leaves your hand. Okay? So it's already going to be moving. It's already going to be moving. So where is your velocity time graph not going to start? 0. So we're going to define uphill as being positive. That's why we're going to have positive numbers coming up like this. So let's start with the position time graph. Roughly, what's the position time graph going to look like? I will give you 3 options. There's option A. There's option B. There's option C. Okay? Sketch. A, B, or C. Could it be B?
No.
No,
Why not?
because it would be like bouncing off something.
No.
And that has constant velocity.
Well, yeah.
But it's
So
accelerating.
B would indicate that you have constant velocity. So if B was right, you would see it go up like this, and then see it come back down like this. Is that what you saw?
No.
No. Clearly, can't be the middle one. What about the inner line of C?
No,
Why not?
because it's accelerating upwards, which is not what we see. Or it's accelerating away from the. You know what I'm trying to say, right?
No.
The velocity like jumps from like being like really positive to being really negative.
Okay. What would, just look at this half of C. If this was it, what would the cart be doing on the way up?
Acceleration.
Speeding up.
Be speeding up. Okay, just don't say
Oh,
acceleration.
oh yeah.
Get out of your minds that acceleration means speeding up. Okay? On the way up, it would be speeding up. On the way back down, what would it be doing?
Slowing down.
Slowing down. This would be the coolest one to watch. Because if you did that, you would push it, and it would go faster, boom, and then it would slow back down right before it got in your hands. This would be cool. Okay? C would be the cool one to watch. Realistically, probably not going to happen. So that leaves us with
A.
A. So, you draw your position time graph, that's what you got. Now, you're going to know the initial position of the cart. You're going to have that data. You're going to know the final position of the cart, where that's going to be. Okay, so so this one is not going to start at 0, 0, unless you happen to be able to push the cart from back like this and have it leave your hand at exactly back here. Okay, tough to do. It's going to be pretty close to 0. It might be farther away if you're willing to go off the front of the cart. But that's going to be the shape of this thing. Now, let's say that you time this thing. And let's say that the total time, just to make up some numbers,
7.
or 2.2, is 2.20 seconds. Now, let me give you some words of advice on timing. You're going to have two people time this event. If there's a big discrepancy in time over this relatively short amount of time, like you have a difference of like a half a second or something like that, here's the default thing. Kids go, oh, we'll just take the average. Like taking the average smooths out all anomalies in the data. No. On that short distance, if you're off by a half a second, one of you can't time. Okay? That's just the reality of it. So when you time events and there's a big difference, just don't, oh, we'll just take the average. No, one of you sucks at timing, okay? Do the trial again, all right? Just don't take this default answer, oh, we'll just take the average. Oh, it was human error in the lab. No, one of you sucks at timing. Okay, so let's say the total time is 2.2. That's the total time. So what we're going to assume is that there is a symmetry to the flight. That we're going to spend half the time going up and half the time coming back down. So if the total time is 2.2, that's going to be 1.1, and that's going to be 2.2. So at 1.10 seconds, what's the velocity going to be?
0.
0. Did this show the Danny's criteria?
Yes.
Yes.
Because it shows it,
Speeding up, or slowing down, stopping, and speeding back up.
yeah, and if you come up here at the top and draw that tangent line, you're going to have a slope of 0 because you have an instantaneous velocity that shows that it's at rest. The tangent lines prior to this are becoming more shallow, they stop, they change direction, and then they get steep. So that's what your position time graph is going to look like. It's just going to be a sketch. You don't know the exact times where it is, so hey, we'll just call it a sketch. There you go. Now, let's talk about your velocity time graph. And at this point, you're going to draw a velocity time graph, but you're not going to know what the initial velocity of the object is. We're going to find it. Okay, that's the whole heart and soul of this lab. So what's your velocity time graph going to look like? I'll give you 3 options. Or none if I can't draw. There we go. There's A. There's B. and there's C. So there's the three options for your velocity time graph. A starts up, curves back down. B is the middle line, diagonal. C is the purple line. So how many vote A? B? 2, 3, 4. C? You want to vote C, don't you?
So I don't think it's right now.
Now, Anna, what does that big sign behind you say?
F equals MA.
Now, when I push this cart, what makes it speed up and slow down? When I push that cart, as soon as it leaves my hand, what's making it slow down and then speed back up? Rhymes with gravity.
That's what I call gravity.
Gravity, right? Do you think gravity provides a pretty constant force? So if my force is constant and my mass is constant, that's why it's got to be that boring middle line of B. You want to think it has a swoosh to it because of Nike. Okay, I blame Nike. Because you go, oh, it's speeding up and it's slowing down. Remember, the only way that you can have a curved line on a velocity time graph is if your force is changing. Okay? If we had rocket engines attached to it or something like that, yes, we could generate those lines. But we don't, okay? We just have to rely on gravity. Now, if you want a boring app, develop the gravity app that tells you the strength of the Earth's gravitational field each day. It isn't like you wake up and you look at it like, oh, it's a low gravity day. I might be able to dunk today. Okay? Or, oh, man, it's a strong gravity day. Ah, man, I can't get out of bed. Sorry, Mom, can't get out of bed to clean the house. It's a strong gravity day. Look at the app. Okay? No. Okay? It's pretty much a fixed value. So, boring as it is, and you all want to think that we'll get creative and we'll have like these nice lines, and we're not. Okay? But that's okay. It's good that we have a constant gravitational field. Now, here's what's going to frustrate you all. You're going to draw a line, and you're not going to know where to start the line, because you don't know what the initial velocity is. Don't care. Just come up here. All you're going to do is you're going to pick a point, and you're going to draw a straight sloping line down like this. But you are going to know the times. How, on this data set, if the total time is 2.2, how long is it going to take for that velocity to go to 0?
1.1.
1.1. So this is going to be half your time. Okay, so you're going to know the time. Okay? Now, let's say that the initial position of the cart, this lays this out in centimeters. Make sure you convert this to meters, by the way. So let's say at the bottom of the cart, you are at 0.10 meters, and it goes up to 1.10 meters. Now, we're going to have to talk about displacement, not distance. Displacement. How do you calculate displacement? What minus what?
Final minus initial.
Always final minus initial. So on the way up, and we're going to look at this in two distinct halves, okay? On the way up, what's my initial position?
1.1.
0.1. What's my final position?
1.1.
So what's my displacement on the way up?
1 meter.
1 meter.
1 meter. On the way down, what's my initial position?
1.1.
What's my final position?
0.1.
What's my displacement on the way down?
-1.
-1. So I'm going to have a positive displacement on the way up, a negative displacement on the way down. Now, here's the heart and soul of this lab. We know that's 1.10 seconds. Now, this is what we talked about yesterday. How does displacement fit with this velocity time graph?
It's the area.
That's the area. So this area in this situation would be 1 meter. Because we don't know how far it's going to go up. So we're going to know the area. Cool. Okay? Now, here's the next big thing. How do you find the area of a triangle?
1/2 base times height.
Area equals 1/2 base times height. Now, you're going to be running with the big dogs in this physics class. Solve the equation first before you put in the numbers. You're not in an Algebra 1 class when you put in the numbers and then solve it. Solve the variable, okay? So you're going to know the area because you're going to know the displacement. You're going to know the base because you're going to know the time. So I need to solve this for height. So, Preston, what does that look like, solve for height, keeping in mind that I loathe fractions with all of my being?
2 times base times area.
Close. How about 2 times area, get rid of the fraction, multiply by 2? How about 2a over b equals h?
Yep.
That too. Okay. Now, when you do labs, and you're going to do a lot of labs, you have to get out of the mindset that a lab is about getting an answer and writing that down. A lab is more important that you show the procedure. Someone should be able to look at your calculations and know exactly what to do. What you have done, the steps, the units, the numbers, everything. It is not just about, oh, here's an answer. You are trying to convey to people, me, that you know what you're doing, okay? There's a methodology to what you're doing. So in this situation, I would take 2 times 1 meter, and then I would divide that by that time of 1.10 seconds. Now, what units am I going to get out of it?
Meters per second.
Meters per second. Ooh, winner, winner, chicken dinner. What's measured in meters per second?
Velocity.
Velocity. So how does that height relate to,
It's your initial velocity.
that's my initial velocity. So once you find the height of this triangle, you have found V naught. So we can't measure it directly, but we can find the area of the triangle. We can find the area of the triangle and we know the base, we can find the height. The height represents the initial velocity. Okay. Now, next thing you want to do is you want to find the acceleration of the cart. Now, later on you'll see that there's a whole bunch of different ways you can calculate acceleration. Here's kind of the opening solver. How does acceleration, whoa, that got weird. Let's bring all that back. How does acceleration relate to that velocity time graph?
It's the slope of the line.
It's the slope of the line, right? So you're going to find the acceleration. If you're a slope person based upon graphs, at this point you're going to know 2 coordinate systems. One point is going to be 0 and 1.11. The other one is going to be 0 and whatever your velocity is. Find the slope of the line. You're using those 2 points, change in y over change in x. If you like that, cool, go with it. Fantastic. If you're a formula person, and later on you'll see where this comes from, but you can also do a equals v minus v naught over time, which oddly enough is just the slope because it's change in y over change in x. Okay? So you also want to calculate the acceleration. Now, here's the story. On the way up, based upon a cursory look at this graph, what's going to be the sign of your acceleration?
Negative.
Negative. Okay? Cool. Now, on the way down, we're going to look at the way down as a completely separate trip. So on the way down, on the way up, we started with a positive velocity that went to 0. On the way down, we're going to start at 0 and end up with negative velocity. Okay? So positive velocity on the way up, negative velocity on the way down. We go from positive number to 0, and then we're going to go from 0 to a negative velocity. So At the beginning of this, everyone's cool. Oh, I have negative acceleration on the way up. The whole point of this lab is to force you to look at the acceleration on the way down. Okay? Cool with that. Stop that camera for a second.